everybody. Today we're going to discuss section 2.2, which is the last section that we will discuss in chapter 2. And this is all about the law of total probability and Bayes' rule, section 2.10. The thing about Bayes' rule I'm going to kind of bring up is that we often times the most of the statistics that you'll be exposed to in undergraduate is what we call frequentist statistics. And what a frequentist does is they use they get a lot of data and they kind of look based on the frequency that something occurs. They get the probability value for it. It helps them make inferences about a population based on the frequentist, how frequently something occurs. Bayes is a whole other area, and probably one of the hardest classes I took in grad school was a Bayesian statistics class. So there's two trains of thought in the statistical world. There's the frequentist frame of mind, and there is the Bayes frame of mind. Like I said, frequentists look at things from the perspective of how often does something occur, essentially. That's very basic, but that's pretty much what it is. Bayesians say, hey, I have a pretty good idea about the probability of something that happens, or they know an expert in an area that knows what the probability of what they call a firm guess might be. And they take that probability and along with another, with a conditional probability after collecting some data, and then they can find out the true conditional probability based off of something else occurring. You'll see what I mean when we see the formulas, but for now, that's pretty much what it is. Frequentists are about frequency. Bayesians are about a prior guess to bet on a probability and then use data to update. So what a Bayesian does is constantly can update their probability so it can change when you get new data, which is some people really like that. It's actually pretty cool. And there's some things that Bayesians can do or claim that frequentists can't claim in their stuff, but that's for a whole nother class. So let's get into the total law of probability and Bayes' rule, some of the basics. So we're just talking about the really basic concepts here. So the total law of probability and Bayes' rule, here's our first definition. So say for some positive integer k, we let the sets b1 through b sub k be such that the set of the sample space is equal to the union of all of those individual sets, and the intersection of any two sets with from b1 to b sub k is equal to the empty set, meaning that meaning the intersections are mutually exclusive. It's kind of one of the requirements, if you will. All right. Then the collection of those sets is considered to be what we call a partition of S of the sample space. So it's like we took an entire sample space, or like a Venn diagram, if you will, and I'll show you one here shortly, and we've broken it down into different partitions, all right, based off of something that we're interested in. All right, so that's just the definition. So let's move on to the total law of probability and Bayes' rule. So if A is any subset of the set S, all right, and B1 through BK is a partition of that set, of that sample space, A can be decomposed as follows. We can decompose it as A equals A and B1, union A and B sub 2, union ... all the way down to A intersect B sub k. We can get a bunch of intersections, essentially. All right. Note this, since we've got B sub 1, B sub 1, B sub 2, comma ... through B sub k is a partition of the sets. A1 intersect B1, or really just A intersect, sorry, not A1, intersect A, and A intersect B2, and dot 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 A intersect B sub K are all mutually exclusive, since the B sub K's are mutually exclusive. All right, ME for mutually exclusive. Thus, A really equals, when we think about back to our multiplication rule from section 2.8, when we have an and we don't know whether they're independent or not, then A is really equal to the probability of A given B1 times the probability of B1 plus the probability of A given B2 happens times the probability of B2 plus dot 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 plus probability of A given B sub K happens times the probability of B sub K. All right, let me write that a little clearer. All right, which equals the sum of I equals 1 to K of the probability of A given B sub I times the probability of B sub I. This is known as the total law of probability. All right, and remember this part right here, what I did to change it comes from the multiplicative law of probability. That's how I got this, this, and this. Basically, I rewrote the A and B1, A and B2 became these guys. Okay. And this is what we call the total law of probability when you have things partitioned into sets. All right. And for 3 partitions, this is kind of what your Venn diagram might look like. This whole area with the first curvy line to the left of the first curvy line is all B1, and then the shaded in area here represents the intersection of those guys. All right, so that's kind of how you would picture one of these. It's not always intuitive at first how this works, but it takes some time to kind of grasp onto this a little bit. All right, so nonetheless, the total law of probability is this. So sometimes we have this information given to us where we're given some conditional probabilities and what we call prior probabilities. The B sub i's are called priors. More on this in a few minutes when we actually do the full out Bayes rule. This is just part of the Bayes rule. Usually this probability of A formula here represents the denominator of your Bayes rule, and we'll see that here in a minute. Okay, so let's do an example using the total law of probability here. Okay, so we've got the members of a consulting firm rent cars from 3 rental agencies. All right, 60% from agency 1, 30% from agency 2, and 10% from agency 3. If 9% of the cars from agency 1 need a tune-up, 20% from agency 2, and 6% from agency 3, what is the probability that a rental car delivered to the firm needs a tune-up? So we've been given some information here. I'm going to call the probability that we get cars from a specific agency A1, A2, A3, or A sub 1, A2, A3. So probability that the car came from A sub 1, or that we rented that car from there, is 0.6. The probability that we rented the car from the second agency is 0.3. And the probability, so it's that and that, probability that comes from the third agency is equal to 0.1. All right, so that. The rest of this information is conditional probabilities. All right. So, for example, this 9% here represents that the car needs a tune-up, given that it came from the first agency. So the probability that the car needs a tune-up, given it came from A1, is equal to 0.09. The probability that it needs a tune-up and it came, given it came from agency 2, is equal to 0.2. And the probability that it needed a tune-up, I'm using T for tune-up, given A sub 3 came from agency 3, is equal to 0.6%, so 0.06. Okay. So we're really looking for the probability that the car needs a tune-up. So just probability of T overall. According to the rule we saw, this should be equal to, on the previous slide here, we've got A given B sub I. So we've got some conditional probabilities going here. So it's really equal to the probability of you need a tune-up given you came from agency 1 times the probability you came from agency 1 plus the probability that you need a tune-up given it came from agency 2 times the probability of that it came from agency 2, and finally add to get to that the probability that it needed a tune-up given it came from agency 3 times the probability of agency 3. So just, figuring out what your givens are and what you have at your disposal when you see this much information kind of helps you figure out that you need to use this. And the fact that you're given so many conditional probabilities is probably a dead giveaway that it's either a total law probability problem or a Bayes rule problem. Okay, so let's just finish this out by plugging and chugging. So this is 0.09 times 0.6 plus 0.2 times 0.3 plus 0.06 times 0.1, and that gives us the loving number 0.12. So there's a 12% chance that if we get a car random from any one of these agencies, there's a 12% chance that it will need a tune-up. Okay, so that's a nice little simple example. Now that, like I said, that what we just calculated, if we were looking to use Bayes rule in its full out form, and this is Bayes rule right here. All right, this is Bayes rule. Assume that we still have our partitions B sub 1 through B sub k of the set S, such that any probability for the B sub i's is always greater than 0 for I equals 1 to k. Then for any event, we want to find the probability that we view one of the partitions, the B sub j's this time is what they're calling it, given A, is equal to the probability of A given B sub j plus times the probability of B sub j in the numerator. And in the bottom is the total law probability. It's the sum of it. We view any event A given any B sub I partition times the probability of that part of B sub I. Now, I don't know how well the book goes into this, but from when I learned this, there's some things going on here, some terms that are used sometimes for some of these things. Remember how I said you use prior information to figure out new information? And here's how this is doing this. So these B sub j value and the B sub i's down bottom are what we call prior probabilities. These are probabilities that we know for certain, or we have a pretty good guess about prior to doing one of these problems. In the problem we just did, for the tune-up, the probability, we knew the probabilities we knew the probabilities that of where the car, what agency the car came from. All right, those were our prior probabilities. These guys here, the conditional probabilities in the formula are called likelihoods. It's the likelihood that we see the outcome given we already know that our prior probability has occurred. All right, so that's what we call a likelihood in statistics. And then we're finding this guy over here, which is called, it's also got a name, it's called the posterior. Let me write that a bit clearer than that, folks. The posterior probability. And what you'll notice here when we do this next problem, or next example, is that often we know enough information about the likelihoods and the prior probabilities. That's information we can usually get. In real life, sometimes it's hard to figure out we may know, say, this probability right here, that particular likelihood, because it's something we can find. What Bayes allows us to do is then come over here and figure this guy out based on the fact that we know this other information. And so we can get to what we call the posterior probability from that specific. Knowing what we know, we can find out what we don't know. Notice that these are just flip-flops of each other. The one in the formula is A given B sub j, and on the outside it's B sub j given A. All right. So we've got, usually you'll be asked to find this in the question, and that's usually not the information given to you in the problem, and that's usually another dead giveaway that you're looking for or looking to use the Bayes rule. All right. So let's move to a new example here. 1% of women at age 40 who participate in routine screening have breast cancer. 80% of women with breast cancer will get positive mammograms. 9.6% of women without breast cancer will also get positive mammograms. So they're asking us two different questions down here. It says a woman in this age group had a positive mammogram in a routine screening. What is the probability that she actually has breast cancer? Okay. And then the second question says a woman in this age group had a negative mammogram in a routine screening. So positive here, negative here. What is the probability that she actually has breast cancer? So we've got some information there to help us out. So let's look and see what was given to us. So it's saying here that in our original part of the problem here, it says in routine screening, women who are age 40 who participate in routine screening have breast cancer. 1%. There we go. Well, that's 1% of women have breast cancer. So the probability that someone has breast cancer is 0.01. That's given to us. All right, that means the probability that you don't have breast cancer is the complement of that out of the women aged 40 who participate is 0.99. Okay. Now it says 80% of the women with breast cancer, so given you have breast cancer, will get positive mammograms. So we're going to do this. We're going to call it probability. This is conditional. Given you have breast cancer, the probability that you will get a positive mammogram, positive, we use plus here for this, is equal to 0.8. It says 9.6% of women without breast cancer will also get positive mammograms. So the probability that someone gets a positive mammogram given that they actually don't have breast cancer is 0.096. All right, so we have all this information here. Okay. So how can we use this to answer our questions? So what's this first question really asking us? It's saying a woman in this age group has a positive mammogram. So that's a given. They have a positive mammogram. That's the given. In a routine screening, what is the probability she actually has breast cancer? So we're looking for B given plus, all right? B given positive, which according to the Bayes rule is equivalent to actually the probability that the person has breast cancer and they have a positive result divided by the probability that they have a positive result. Okay. And remember, the denominator here is the total law of probability. We're gonna have to figure that out as we go. So the top really is the opposite of the thing we're trying to find, which is something we already know, and that's the probability that it's positive given they have breast cancer times the probability they have breast cancer. The denominator in this case is going to be that same thing we have in the top. That'll be one event we have. The probability that we get a positive result given the person has breast cancer times the probability they have breast cancer. But we also have to add in the opposite of that, which is the probability that they test positive given they don't have breast cancer times the probability that they don't have breast cancer. All right, I'm just going to say cancer from here on out. I think I'm feeling silly saying the word breast cancer over and over and over again. All right, so what do? We just plug in our numbers. We've got positive given B is 0.8 times the probability of having the cancer, which is 0.01, all divided by 0.8 times 0.01 again, because we just repeat the top again, but we add to it the probability that the person is positive and doesn't have the cancer, which is 0.096 times 0.99, which is the probability they don't have the cancer. And when you do that all together, this comes out to approximately 0.0776. So there's like a 7.8% chance, roughly, probability that you have breast cancer given you've tested positive. All right, which sounds weird, right? So we've got to solve the other one as well, but it's very similar to this one, with the exception of we are missing some information here. All right. But we can decipher the information from stuff we already know. Okay. So I'm going to erase this bottom piece. I'll give you just a second if you're writing it down. Hopefully you can see everything okay with my chicken scratch. We're going to keep the probabilities we have up there, but we're going to redo this for the second part. All right. So we've got the following. We know this information above, but what this second thing is really asking is the probability of a woman in this age group having a negative mammogram in a routine screening. What is the probability that she actually has breast cancer? All right. So it's given that it's given that the screening was negative. So we use a negative symbol here. But we don't know the probability they actually have breast cancer if they got a negative screening. And it probably goes as no surprise, the reason you would want to do this in medical science is to see how good your testing programs are for these kind of things. And so that's why we do problems like this. This comes in handy a lot in the medical field. So this should be equal to the probability, the opposite of what we just wrote down. All right, so the probability that it came out negative given B times the probability of having the cancer, all over the same stuff, negative given they had breast cancer times the probability they had breast cancer, plus the probability it was negative given they don't have breast cancer, times the probability that they did not have breast cancer. So we know some of this information, but we don't know all of it. So up here, I want to make a special note of something. The positive given B and the positive given not B are useful to us in this case because the complements of those two events are the fact that they would be negative given they had these things. So for example, the probability that it's negative given the person had breast cancer should be equal to 1 minus 0.8 or 0.2. The probability that the test was negative or the mammogram was negative given they did not have the breast cancer should be 1 minus 0.096, which is roughly 0.904. So we have those bits of information there even though we didn't know they were there. So now we can fill this problem in and finish it out. So I got negative given breast cancer, which is 0.2, times the probability that the person had breast cancer, which is 0.01. I'm looking over here. Divided by that same stuff, because it's the same thing in the first part of the equation, or the addition part in the bottom. 0.2 times 0.01 plus the negative given they didn't have the breast cancer, which is 0.904, times the probability they didn't have breast cancer, which is 0.99, which is equal to 0.0022. Now I ask you, is that a good probability to get for this kind of situation? Because remember, we're trying to find the probability the person has breast cancer given their mammogram didn't tell them that. All right. And so 0.022 is really 2.2%. So there's only a 2 point, actually no, sorry. My bad, I'm doing my math wrong. It's really 0.22%. So that's a really small chance that you have breast cancer and the thing told you you didn't. That's pretty good, actually. That's actually better than what we found with the probability that the person had breast cancer given the test came up positive. So a negative, what we call they call this a false negative. In other words, it gave a negative reading when it should have given a positive result. It's either called false negative, false positive. I lose my mind with those terms sometimes because I don't use them often. But nonetheless, there's your answer. Boom. All right. Let's do another example. All right. Hopefully everybody's kind of following along so far. Example 3. We're going back to the thing we used the total law of probability on example 1. All right, so we got the members of the consulting firm that rent cars again. All this information is the same. We've got the probability came from agency 1 is 0.6. The probability that came from the car came from agency 2 is 0.3. And the probability that came from agency 3 is 0.1. And then we had our conditional probabilities that it needed a tune-up given A1 equals, what was it, 20%, so 0.2. Oh, no, not 20%. That's agency 2. Agency 1 was 9%, so 0.09. Probability needed a tune-up given A2 is 0.2. And then lastly, we have probability that came from, needed a tune-up given it came from A3 was equal to 0.06. All right, we don't need all that information to answer this question since we've already done basically the total law of probability already. So if the car is delivered to the firm, needs a tune-up, so it's given it needs a tune-up, what is the probability it came from agency 2? So remember, just like in the last problem, we're going to flip-flop this around in the numerator. So we're looking for the probability that needed a tune-up given it came from agency 2 times the probability it came from agency 2. In the bottom, we need the total law of probability, which we can, since we've already solved this, it's really just probability of t from the previous page, but I'm going to write it out anyway. It's the probability of t given A1 times the probability of A1 plus the probability of t given A2 times the probability of A2 plus probability of t given A3 times the probability of A3. Now remember, that was the probability of t. Okay. I'm going to erase that. All right. So this just equals. We just fill in the blanks or the values we need, and so we got probability of t given a2 is 0.2. Probability of a2 is 0.3. That's our numerator. In the denominator, I'm going to recall back because I figure you guys can plug in the numbers here and add. But this ended up equaling 0.12 in the last problem, in example 1. So we have 0.2 times 0.3 over 0.12, which ends up meaning we get a 0.5 as our final answer. So there's a 50% chance that the car came from agency 2 given it needed a tune-up, which kind of, doesn't feel like it makes sense when you see that probability and you look at the fact that only 30% of the cars came from agency 2, but this is given that it needs a tune-up because 20% of the cars from agency 2 needed a tune-up, so it kind of works itself out. All right. Example 4, the diabetic example. All right. Get my notes over here because I don't like to work without a net. So in a certain community, 8% of all adults over 50 have diabetes. If a health service in the community correctly diagnoses 95% of all persons with diabetes as having the disease, and incorrectly diagnoses 2% of all persons without diabetes as having the disease, find the probabilities that the community health service will diagnose an adult over 50 as having diabetes, and the probability that a person over 50 diagnosed by the health service as having diabetes actually has the disease. All right, so we've got two fairly different questions here, but I'm going to start this out by saying, let's let A denote that the person has diabetes. And let's let the term B, letter B, describe the person is diagnosed with diabetes. Okay. So we're given some information up here above. It says in a certain community, 8% of all adults over the age of 50 have diabetes. So we know the probability of A is equal to 0.08. All right. We also know some other information. It says if a health service in the community correctly diagnoses 95% of all persons with diabetes. So this is the probability that we correctly diagnose the person given they have diabetes. It's equal to 0.95. And then we also know that the probability that is 2% that the person was diagnosed with diabetes. In other words, they were incorrectly told they had diabetes. You have to watch the wording on some of these problems from this textbook. They try to be tricky. And so, of all persons with diabetes having the disease incorrectly diagnosed, so it's saying that 2% of the people were diagnosed with it when in fact they didn't have diabetes. So probably B given not A is equal to 0.02. And we also know, because we know the probability of A, the person having diabetes, is 0.08, the complement of that is the probability A complement, or 1 minus 0.08, which gives us 0.92 for that. So again, the first part, this first question here, is what I'm going to do first. And it says, the community health service will diagnose an adult over 50 as having diabetes. All right. What's the probability that the person will diagnose them as having diabetes? All right, so we're really asking what's the probability of B. We're going to use the total law of probability here. So really these two parts are helping each other out. So the probability of B in this case is going to be the probability that the person was diagnosed given that they had diabetes times the probability they had diabetes plus the probability they were diagnosed with it given they didn't have it times the probability that they didn't have it. Okay. And we can just plug and chug here. It's 0.95 for the B given A, times 0.08 for the A, plus 0.02 for the B given not A, times 0.92. And that gives me a whopping 0.0944. So that's the answer to part A, or the first part. The second part is actually using Bayes' rule in its entirety. So it says a person over 50 is diagnosed by the health service as having diabetes. So given that you've been diagnosed with diabetes, what's the probability they actually have the disease? So part 2 is really asking us the following. Probability that we were diagnosed with it, or that we have it, given that we were diagnosed with it. Which, using Bayes' rule again, the flip-flop of this goes in the numerator, probability of B given A, times the probability of A. And since we've already figured out the denominator in the first part of this question, I'm just going to write probability of B down here, and we'll utilize that to save ourselves some time. So the numerator, we're going to have 0.95 for the probability of B given A times 0.08. In the denominator, we're going to have that 0.0944, and this equals 0.8051. So the probability that someone has the disease given they were diagnosed with it is like roughly 80.5% chance that happens. So that's pretty good. That means their testing is not 100% great, but it's not completely terrible either. It's pretty damn good, I would say. So that's the law of total probability and Bayes' rule. This may seem simple after seeing so many examples of it, but I will promise you that if you ever take a Bayesian statistics class in grad school or somewhere else, this stuff gets a lot crazier. This is just the tip of the iceberg. This is what the foundation of what it's built on, but it gets a lot worse. But it's still fun and interesting. So anyway, here's the recommended textbook exercises. We're done with chapter 2. We will have 2 more videos from the first couple sections in chapter 3. But you should be able to do homework number 3 at this point. And hope everybody's doing well, and I'll talk to you later. Bye.